so let's get back to where we were previously. We just started off with the Nyquist stability criteria. So what is this Nyquist stability criteria? The question is, we are essentially trying to figure out information about the stability of the closed loop system by looking at the frequency response of the open loop system. That is what essentially the Nyquist stability criteria boils down to. I think in the last class I wrote all these things down. I am just restarting from the same place, right, and I left you with a question, right. So that is what we are trying to address today. Okay. So let us consider the standard negative feedback system. Okay. G of s being the forward path transfer function, h of s being the feedback path transfer function, g of s, h of s being the open loop transfer function, and the closed loop transfer function is going to be y of s divided by r of s, which is going to be g of s divided by 1 plus g of s h of s, right. So consequently the closed loop characteristic polynomial is going to be 1 plus g of s h of s. And why is this important? The roots of this closed loop characteristic polynomial are the closed loop poles, right. So the open loop transfer function g of s h of s, let us consider it to be represented as no of s divided by d of s, right. That is essentially saying that the open loop transfer function is a ratio of two polynomials in S, right. So consequently I can rewrite this closed loop characteristic polynomial 1 plus g of s h of s as 1 plus no of s divided by do of s, which is do of s plus no of s divided by do of s. Okay, so that is what we have, and we are particularly interested in the numerator. Why? Because the roots of the numerator polynomial are the closed loop poles, right. So please recall the zeros of 1 plus g of s h of s are the closed loop poles, right. So that's important for us, right. So but the poles of 1 plus g of s h of s are the open loop poles, right. So why? Because if you look at the denominator of the polynomial 1 plus g of s h of s is do of s, right. Do of s is nothing but the denominator polynomial of the open loop transfer function. So consequently you will see that this is going, the poles of 1 plus g of s h of s are going to be the open loop poles. Okay, so that is what we have, right. So that is something which we already identified. Now the question that we are asking ourselves, the place where we stopped last class was that, can I comment on the location of the closed loop poles, which in turn is saying that, okay, can I comment on the stability of the closed loop system by plotting the frequency response of the open loop system, okay, or the open loop transfer function, right. So question is, can I plot g of j omega, h of j omega as a Nyquist plot, right, the Nyquist plot of that, and then from that comment on the stability of the corresponding closed loop system. Okay, that's the question we are asking ourselves. All right. So the in order to answer that question, okay, the first concept we are going to look at is what is called as a mapping theorem. Okay. So let's look at this theorem. Okay. So what does this theorem tell, and how are we going to utilize this theorem for our purpose? Okay. So that's something which we do. So let's go to the handout, which I already shared on the course website, right. So if you look at this mapping theorem, right. So what are we saying? So let me essentially read it from here. So we are saying, let f of s be a ratio of two polynomials in S. Okay, so I am discussing this mapping theorem. Okay, that's what we are discussing, right. So let f of s be any polynomial, a complex valued function, right, which is in turn a ratio of two polynomials in S. Okay, it has a numerator and a denominator. Okay, let a closed contour in the S plane contain z zeros and p poles of f of s without passing over any of the poles and zeros of f of s. Okay. So that is what we are considering. So what I am doing, I am considering a closed contour in the S plane. Okay, that means that any shape, okay, any arbitrary shape that essentially is a contour in the S plane, but does not pass over any of the poles or zeros of this function capital F of s. Then this closed contour in the S plane is mapped to a corresponding closed contour in the f of S plane, because see, if you have a path in the S plane, obviously we are going to have what to say, at each and every point in the contour a particular value of S. That value of S you can substitute in f of S, obviously you will get a corresponding value in the f of S plane. So you can map it to the f of S plane, right. So once we do that, what is going to happen? What's going to happen is that we are going to get a corresponding contour in the f of S plane, okay. Then what we do is that we count the number of clockwise encirclements of the origin by the contour in the f of S plane, okay. We will see how to count these encirclements, okay. What is meant by an encirclement and how do we count them, okay. So now if I count the number of clockwise encirclements of the origin by the contour in the f of S plane, that's going to be equal to z minus p, okay. What were z and p? Z was the number of zeros of f of S within the contour in the S plane, okay. P was the number of poles of the function f of S which was contained within the contour in the S plane, okay. So z minus p would be the total number of clockwise encirclements of the origin in the f of S plane of the corresponding closed contour, right. So let me illustrate what this is, okay. So we have read the statement, so let's say we see what it means, right. So we have a function, so let's say consider a complex valued function f of S, alright. So that's what we are essentially doing. So what we are saying in the mapping theorem is that first you give me the S plane, okay, I take the S plane, okay, and I take any contour, let's say any arbitrary contour in the S plane, okay. Okay, this is a closed contour in the S plane, is it not, right. So obviously in the S plane you need to mark the number of poles and zeros of f of S, right. That's what we have been doing till now, right. So what this theorem says is that, so this is going to be mapped into a corresponding contour in the f of S plane, okay. So let's say, like some arbitrary contour, let's say for the sake of argument, let's say f of S has let's say 2 poles here, right, and let's say 0 here, okay. So if I take this green contour, which I have arbitrarily drawn, right, so what are the values of z and p? Z should be the number of zeros of f of S within the contour, right. P should be the number of poles of f of S within the contour. So in this particular example, z and p are both 0, right. So what is going to be the number of encirclements of the origin? It is going to be 0 because z minus p, right. So I will have some arbitrary contour in the f of S plane which may be like this, something like this. I am just drawing an arbitrary contour, okay. So which essentially gets mapped this way, okay. This S contour gets mapped to this f of S plane and it will be this way, okay. Now on the other hand, let us say I take a contour, like which essentially is like this, okay. So what happens here? So in this case z was 0 and p was 0, right. In this case what happens? What are z and p? Z is 1, p is 2, right, within the contour. So what is z minus p? Minus 1. So what does a negative value mean? That means that, see, what was n? N was the number of clockwise encirclements of the origin. A negative value means, it is anti-clockwise or counterclockwise encirclement. That's what it is, right. So this black contour may be mapped to something like this. I am just drawing an arbitrary shape, okay, without. So you see that if you stand at the origin, it is encircling the origin once in the counterclockwise direction, okay. That may be the mapping here, okay. So what this mapping theorem essentially says, if we write the mathematical statement, it essentially says n is equal to z minus p. Okay, so that is the equation, okay, the mathematical statement of this mapping theorem. Okay, it essentially says that, look, you know, like if I have a closed contour in the S plane which does not pass over any of the poles or zeros of f of s, an arbitrary function f of s, then that contour in the S plane gets mapped to a corresponding closed contour in the f of s plane, and the number of encirclements of that contour in the f of s plane in the clockwise direction n is going to be z minus p. And what is z? Z is the number of zeros of f of s within the closed contour in the S plane. P is the number of poles within the closed contour in the S plane. Okay, so that's what this mapping theorem is about. Okay, n is equal to z minus p. Okay, so please remember that. Okay, yes. Yeah, so typically you would take a clockwise contour, okay. So yeah, it can get mapped to a clockwise or counterclockwise contour, okay, like depending on the function, right. Z minus p is 0, that means that number of clockwise encirclements of the origin in the f of s plane is 0, that's what it is, right. So that's what happens, right. Yeah, you can have. Yeah, we are going to look at examples. Exactly. Okay. Yes. Capital N is the, okay, let me write down the meanings of all these terms. Okay. So capital S, okay, is essentially the number of zeros of the function f of s within the closed contour in the S plane, okay, that's Z, okay. What is P? P is the number of poles of f of s that lie within the closed contour in the S plane. Okay, that is P. Okay, so N is the number of clockwise encirclements. Okay, of the origin in the f of s plane, okay, of the origin by the corresponding contour, okay, in the f of s plane, right. Okay, so you map a closed contour in the S plane to a corresponding contour in the f of s plane, and then you get this result. Okay, so that's the mapping theorem. If the value of n is negative, that means it's counterclockwise. N is positive means it's clockwise, right. If n is 0, there is no encirclement. Okay, so that's what it means. Okay. Oh, no, that is different. Okay, good point. Okay, good point. You know, like so. Okay, so that's a good observation. So let me just maybe use a different n here. Okay, let me put NC. Okay, some n contour, right. So okay, did we use Z and P for something else? Right? I don't recall, right. Okay, I hope everyone understood his question. You know, like this is not the same capital N as we wrote for S power n in type 0, type 1, type 2 system. Okay, this is different. Okay, so that's why I'm just putting NC. Okay, that's a good observation, right. Okay, yeah. Okay, so let's look at some examples. Okay, so that's what I have presented in the handout. Okay, in the handout, you know, like essentially what I have done is the following. I have just taken this particular function for f of s. Oops, what did I do? Right. So essentially one may wonder why this example has been taken, I will explain to you once we discuss, okay. So let us say we take f of s to be this function, okay, which has 2 zeros at minus 1.5 plus or minus 2.4j, right, and 2 poles at minus 1 and minus 2, right. Let us look at the function f of s in that form currently, right. Now anyway, of course I had given the reference as Ogata, okay, so this example has been taken from that book, right. So if you look at the first figure, right, so where can you see the 2 poles, like the 2 poles are at minus 2 and minus 1, right, so we already know that, right, and the 2 zeros are at our complex conjugate at these points, okay. So to begin with, if you take a contour A, B, C, D in the S plane, okay, it so happens that if you plot it, okay, I leave it to you as an exercise, okay, to do it in MATLAB, you take an corresponding contour. This is not a closed contour, by the way, okay, we are not analyzing mapping theorem yet, right. So this is an open contour. If you look at A, B, C, D, it's not a closed contour. You can see that gets mapped to a contour A prime, B prime, C prime, D prime, okay, in the f of s plane, right. So the corresponding character of the prime is the corresponding value in the f of s plane, right, and we get a different shape altogether, right, that depends on the function, right. So similarly, if you have the contour D, E, F, A, that gets mapped to a contour D prime, E prime, F prime, A prime, okay. So that's how it just turns out, right. So now if you take a closed contour A, B, C, D, E, F, A, I hope everyone agrees that that's a closed contour in the S plane. Now you can see that gets mapped to the contour A prime, B prime, C prime, D prime, E prime, F prime, back to A prime, okay. So that's what happens with this particular contour, right. How do you get it? Once again, you need to plug in and generate the curve, okay. And is there a gap between these two curves, right? Should there be a gap? Do you think, like when you plot, say for example, when you go from D prime, E prime, will it overlap with this part of this B prime? I want you to figure it as homework, okay. So please do it, then you come back and tell me what your observations are, okay. I hope my question is clear, right. So you see two for example arcs, like which seem to have a constant gap in between, right. Would you have a gap there or would it not be there? If it would not, if it is not there, what is the reason, right? So I think you need to figure it out, okay. Please take this, take an arbitrary contour, okay, and map it, right, using MATLAB. Yes.
How are you representing contour with this rectangular diagram?
How do we?
You're representing something with a rectangular diagram.
We are just taking some arbitrary contour, okay.
What does contour mean?
Contour is just a curve, right? It's just a domain in the S plane.
Is it like an input?
It's not an input per se. It's an input to this mapping theorem, right? So that's it. So it will give you a set of values of S, right? Would it not?
So what is A in this case?
A is a point. See, A is a point. Let's say you start from -3. S equals -3 is A, right? That's it. Okay. You just draw an arbitrary contour and give some values of yes, and then plug into f of s. You know f of s already, and then generate that contour in the f of s plane. Yes. Okay. Good point. We are going to answer that, right? How is this useful? That's something which we are going to learn. How are we going to apply it to our subject, which is control systems? Okay. That's a good question. We will come there. Okay. So please bear with me for another 5 minutes. Okay. I will explain this. So now within this closed contour in this S plane, how many zeros and how many poles of f of s are present? What are the values of z and p? Z is 0, right? Because the 2 zeros lie outside, right? What is the value of p? 2. So what is z minus p? -2. So now you stand at the origin in the f of s plane, right? And then start counting the number of encirclements of the origin as you stand at the origin in the f of s plane and sweep through the entire mapped contour in the f of s plane. So you look at it, you draw a vector from the origin to A prime, which is your starting point, and then start sweeping. So if you come to A prime, B prime, C prime, D prime, you have one encirclement, right? You would have rotated 360 degrees around the origin in the counterclockwise direction. Let's not worry about the magnitude changes, but then the angle will come to 360 degrees. Do you agree? Now you go D prime, E prime, F prime back to A prime, you sweep another circle, another 360 degrees, right, in the counterclockwise directions. So how many counterclockwise encirclements do we get? 2 in the f of s plane, right? So what should be the value of n? C minus 2, and that's what you get from the mapping theorem, right? So the mapping theorem says that n subscript c should be z minus p. So z here in this example was 0, p is 2, so z minus p becomes minus 2, and that's what you can observe from the diagram in the f of s plane. Okay. In figure D, if you look at it, the entire contour has been stretched a little bit so that you enclose both the zeros within the contour, right? So now what are the values of z and p? 2 and 2. So number of encirclements should be z minus p should be 0. So you look at it, you look at the map contour in the f of s plane. Does it encircle the origin? No, right? The map contour does not encircle the origin. Okay, so that's what it is, right? So there are a few more examples. In this case, A, B, C, D has only 1 0. You can have contours like this also, right? And no poles. So z minus p will be 1 here. So you look at A prime, B prime, C prime, D prime, it encircles the origin once in the clockwise direction, because NC will be 1 here, plus 1, right? So you can see that A prime, B prime, C prime, D prime will encircle the origin once in the clockwise direction. If you take E, F, G, H, doesn't encircle any, it doesn't contain any of the zeros or poles, it just gets mapped to E prime, F prime, G prime, H prime. Okay, so that's what happens, right? Yeah.
I think that if NC is equal to say 3, then you still have just one contour. Taking FES point here and mapping it to the FOS plane, you still get just one contour.
But it would have basically encircled the origin 3 times. That's why I'm saying please do it and convince yourself. Okay? Yeah. So because we cannot do it by hand, right? So we need this particular example, you need to use MATLAB or any other numerical tool to generate the contour. So good point. That's why I'm saying kindly program. You know, like I'm sure you guys can do that, right? So just give a sequence of values of s, right? And then take this f of s, calculate f of s, plot it in MATLAB, then you will see how the contour comes up, right? So of course, the finer the the closer the values of s, the more smoother will be the profile in the f of s plane, right? Which you can do numerically and then like convince yourself, right? Please do that. You experiment with different contours. Okay, so that's a mapping theorem.